So in this video we're going to take a look at integration by parts. Integration by parts is an important technique that is often used in engineering and science. It is frequently used to change the integral of a product into ideally simply integral. Um, so what that boils down to. So let me just change the color of the pen here to something that's better. So we know that the dx of a product of a function u and v can be expressed as v du dx plus u dv dx. So when we're differentiating a product of two functions, it's the first function multiplied by the differential of the second plus the second function multiplied by the derivative of the first. And obviously both u and v are functions of x. So let's rearrange this a little bit to get u dv, to make u dv subject of our equation. So u dv dx is the same as d dx uv minus v du dx. Now we can integrate both sides to get an integral of u dv dx and multiplied by dx is the same as integral of d dx uv, let's keep it as a product, minus an integral of v du dx dx. So then we can simplify it a little bit to get that an integral of function u dv dx is the same as uv, which comes from this integral over here, minus integral of v du dx. So I can rewrite it as something more approachable, and which would look like an integral of u dv is the same as uv, product of two functions, minus integral of v du. So this is known as integration by parts. And generally what we want to integrate by parts are functions of the form something like this: x e to the power of x dx, or something like integral of t sine t dt, or even integrals of a form where we have e to the power of theta cos theta d theta. And also integral of x ln x. So wherever there is a product of two functions, we can use integration by parts. Setup is a little bit more difficult than previously, because now we need to be capable of identifying functions that would fit into the integration by parts schema. So given a product of two terms, the initial choice is which part to make equal to u, and then which part is going to be equal to v. So this is the question we're asking: what's u, and also what is v? The choice must be made in such a way that the u part becomes a constant after a successive differentiation, and the v part can be integrated from standard integrals. So we want to be able to integrate that dv into something that we can put into our uv function. And anyway, the following rule holds: if a product to be integrated contains an algebraic term like x or t squared or 3 theta, then this term is chosen as u, and the one exception is natural log of x, which in this case natural log becomes the u part. That's not that important. We're going to figure it out in the examples. So let's take a look at the first one. Let's determine x cos x dx. So I'm going to say, as previously mentioned, that let me change color to black, that u is going to be equal to x, so that leads to du dx equal to 1, and that means that dx, the du rather, equals to dx. So that's all good. And then the second part, so we already identified what's u, so that's this part, and now the second part is going to be my u dv. So cos x dx is dv. So let's change color back to black. Cos x dx is dv. Integral of cos x dx is equal to sine of x, and that is equal to my function v. So now I can put this all together and to get that integral u dv, which is the integral over here, integral that I'm trying to calculate, and I'm going to get that integral of x cos x dx is the same as uv, which in this case is going to be x sine x minus v du, which is an integral of cos x integral of sine x dx, and then we can integrate and simplify to get x sine of x minus integral of sine x dx is the same as minus cos x minus cos x, and then put this together to get x sine of x plus cos of x, and remembering about the constant of integration plus c. So that would be the first example. In the next example, we have to find the integral of 3te to the power 2t squared. So in this case, I'm going to say that u equals to 3t, from which du dt equals to 3, and from here I'm going to get that du equals to 3 dt. Then I'm going to get that dv equals to e to the power of 2t dt. Now I can take the integral of this expression, so the integral of e to the power of 2t dt is the same as half e to the power of 2t, and that equals to my function v. So now I can combine this, so the integral of 3t e to the power of 2t dt is the same as, now I have u v, so that will be 3 over 2 times 3t, sorry, not 3t, 3 over 2 t multiplied by e to the power of 2t, and all that minus integral of half v du, so half e to t, half e to the power of 2t multiplied by 3 dt. And note that the actual magic happens in this case, because now this is just a constant, number 3 is just a constant, which allows us to take it out of the integral sign. Dt is just a sign of further integration, so that makes it really easy for us to integrate this second integral. So when I integrate it all and simplify, I'm going to get on the left hand side the integral, so that will rewrite 3 over 2 t e to the power of 2t minus 3 over 2 integral of e to the power of 2 t dt, and that simplifies to 3 over 2 e to the power of 2t minus 3 over 2 e to the power of 2t over 2, and then obviously plus c. And then I can do a little bit of simplifying. Let me just not forget about that t. So that will turn into 3 over 2 e to the power of 2t in the bracket t minus half and then plus c. So then that resolves this problem. And the next one, we have to evaluate a definite integral between 0 and pi over 2 of 2 theta sine theta d theta. So as always, u will be equal to 2 theta. From this, du d theta equals to 2, and du equals to 2 d theta. And then we have dv equals to sine theta, d theta obviously, and then v equals to integral of dv, which is going to be equal to integral of sine theta d theta, which is obviously minus cos theta. So now I'm going to put it all together so that integral, or before I go into my definite integral, I'm going to calculate the indefinite one. So between 0 and pi over 2, 2 theta sine theta d theta is the same as, so vu, so uv rather, equals to uv 2 theta, minus goes in front, and cos theta minus integral of v du minus minus cos theta 2 d theta. So it's probably noticeable that I can integrate this with relative ease. So when I put this all together, I'm going to get minus 2 theta cos theta plus 2 integral of cos theta d theta, and the integral of cos theta is obviously sine theta. So now I can simplify this fully to get minus 2 theta cos theta plus 2 sine theta and plus c. So that's my indefinite integral, but obviously I have to evaluate this between 0 and 2 pi. So by substitution, I'm going to get minus 2 theta is equal to pi over 2 cos of pi over 2, and then plus 2 from the second expression plus 2 sine of pi over 2, and then I have from this, I have to subtract minus 2 times 0 cos of 0 plus 2 sine of 0. So then when I simplify the expressions, I'm going to get minus 0 plus 2 minus 0 plus 0, which is equal to 2. And that would be the value of the definite integral. Again, what helps me here is the realization that dv is equal to sine theta d theta. So from here I can find the value of v. Finding the indefinite integral is the first step. And then once I found the definite integral, I can put my limits of integration into place and find the result. In the next example, again, I'm dealing with a definite integral between 0 and 1 of 5x e to the power of 4x dx. So again, I'm going to say that u will be equal to 5x. Du dx from here is very straightforward. Dx equals to 5. So then du equals to 5 dx. And that means that dv has to be equal to e to the power of 4x dx. V is the integral of that e to the power of 4x dx, and that is equal to a quarter of e to the power of 4x. So now I have u, I have du, and I have v, so and also I have v. So now I can put this all together to get the integral of 5x e to the power of 4x is uv, which is 5x multiplied by quarter of e to the power of 4x minus integral of v du, so that will be a quarter of e to the power of 4x multiplied by 5 dx. So now I can start integrating, rewriting the first part of the expression, 5 over 4x e to the power of 4x minus 5 over 4 integral of e to the power of 4x dx gives me the result of 5 over 4x e to 4x minus 5 over 16 e to the power of 4x and plus c. So now I can actually take a common factor out of this expression and get a slightly simpler expression. So that would give me 5, sorry about this, so that will give me 5 over 4 e to the power of 4x in the bracket x minus a quarter. And I have to evaluate this between 0 and 1. So this expression turns into 5 over 4 from the for the upper limit for 1, 5 over 4 e to the power of 4 times 1 and the bracket 1 minus a quarter. So that's the first part of the definite integral. From this I'm subtracting 5 over 4 e to the power of 4 times 0 in the bracket 0 minus a quarter. So now I can just chuck it into the calculator and get the result of 15 over 16 e to the power of 4 minus 5 over 16, which is equal to 51.5. The value is quite high because e to the power of 4 is a large number, 51.186. So in the next example we're determining integral between of x squared sine x dx. So again, u equals to x squared du dx equals to 2x, and from here du equals to 2x dx, and then dv equals to sine x. From here v equals to integral of sine x, which is equal to minus cos of x. So now I can do the substitution. So integral of x squared sine x dx is equal to uv, so x squared multiplied by minus cos x minus integral of v du, so that's minus integral of minus cos x to x dx. So now I can start integrating so let's rewrite. This will be equal to integral of x squared minus x squared cos x plus take 2 out of the bracket, 2 integrals of x cos x dx. So obviously this integral here is not a standard integral, but we can use the integration by part again, or we could use some substitution. But also, maybe if you just notice, the first problem that we did today also dealt with x cos x dx, and that integral is x sine x plus cos x. So I'm going to apply that in here to get x squared cos x plus 2, and in the bracket here x sine x plus cos x, and then plus c, and I can expand the bracket and simplify. So I would get, and minus remains here, so I would get minus x squared cos x plus 2x sine x plus 2 cos x. And note that I can rewrite this to get 2 minus x squared, taking common factor out of the cos, and then plus 2x sine x, and obviously plus c. So slightly more involved integral. You would have to do integration by part twice, but we had this example already resolved, so that that should be sufficient.